as long as I'm roughly self-consistent, I guess it's good enough. What I'll try to say is that in a way, regularity detection is the basic property of what the brain does, of what the cortex does, and the basis of acquiring expertise is managing to detect different levels of regularity so that we don't have to, in a way, compute things online, because we're pretty poor at that as individuals, and we can, in a way, have sophisticated, automatic ways to use pre-learned skills in a nice and efficient way, given different circumstances. I'll start the story with what I think is a very, very elegant study of chess players. Chess players, well, in a way, chess playing is something of almost the peak of, you think of, is almost the peak of cognitive or high-level cognitive ability. I'd like to say that in a way, it's just one example of what happens to us, regardless of what the task is, of how complex it is, and what makes us, what makes some of us, not myself, but some of us really chess masters, is the following thing: you learn the scheme. What does it mean? And let me tell you about a very, very nice study that was conducted by Chase and Simon in the 1970s. So chess players, master chess players, have amazing memory. What does it mean? If you show them just in the middle of a chess game, you expose the board for like 5 seconds, then they have to close their eyes and recall the board. They're amazing, which led people to think, aha, playing chess is one thing that makes you very smart, at least in terms of having very broad memory. However, if you use the same chessboard, but you kind of randomly arrange the tools, they collapse completely. They lose all the benefit that they've gained as sort of master chess players. So their memory is very specific, and I think this is a very crucial point, because what made them expert is not like they have a general representation of how the chessboard looks like and how you can, in principle, orchestrate it, but they have a very specific memory that helps them work out the next move. And they're very efficient, and the way, in a way, their memory is organized, that the positions are stored that will make them very efficient, sort of something. Of course, they can't store all possible positions, so they kind of cluster them in a way that will make the next move more efficient. So it's not just an archive, it's something, well, what Tali would like to say, a very complex sensory model plan, because they organize gradually the scheme of chess game into sort of efficient planning of the next move. When people look at, well, they try they ask them to reason about the chess game, the sophistication of their reasoning does not exceed regular chess players. It's not like their online computation is so sophisticated. It's just that the units with which they plan and think are broader units and are more appropriately structured for being very, very good chess players. By the way, general intelligence doesn't differ, so it's not. The idea here is that it's not a general tool for becoming smarter. You acquire a very sophisticated scheme. By the way, any idea how long it takes to acquire this kind of expertise? An interesting figure, it seems to be rather ubiquitous across different levels of different domains of expertise, whether it's like music playing or chess playing. And the sort of, well, it's not like a golden number, but it's an estimate. It's something like, any idea? Plus minus one? Well,
10,000 hours.
To become an expert? It's like 10,000 hours, which means like 3 hours a day for 10 years or something like this. And this is pretty much a general figure, also true for language acquisition and other expertise to which I will address afterwards. What I'd like to say is that the case of chess is a typical example of the dynamics of learning complex, but also simple, cognitive, and not only cognitive, but also perceptual tasks. Chess seems like an oddity, but I would like to say that perception is very similar, and I'll try to give you some examples. The specific examples that I will be given is some few experiments, and I will not get into details, just the idea that we've done in our lab, which is very, very simple tone discrimination, but I will try to show you that very quickly, and also following more practice, what we are implicitly trying to do is get the scheme of what is repeated, rather than online compare the two tones that we are asked to do. I've also tried to say that language acquisition, which of course is much more complicated and takes much more to acquire, follows the same general concept of regularity detection and scheme structuring. I'll also push the idea that there is an anatomical underlying correlate for this process. And the anatomical underlying correlate, this is a brain. Okay? It doesn't come in colors in the natural environment, but the colors are here to make a point. This is the frontal part. Well, this is not just the whole brain, this is the cortex, the cover. And this is the frontal part, and this is the posterior part. And the claim I'm trying to make is that the frontal part is what we do, which is in a way is better for online computation. This is where we deal with novel problems when we have to do things like, well, the schemes are very simple. Novel problems like we have two things, we have to compare between them. How do we compare two sequentially presented something? Stimuli, we have to actually compare. It seems simple, but I think this is in a way the seed of intelligence, because we take one, in a way we retain some information about this element, and then we have to retain it until we have the second element, and then compare. And if we don't have any scheme that helps us so that we don't have to retain this information, we have to do it here. This is where we can retain and compare and do all sorts of things. This is the frontal part. But actually, in parallel, all this time we're looking for regularities, simple and gradually more complex regularities. And when we manage to form some sort of representation, some sort of scheme for these regularities, the processes that govern our performance are really conducted in the posterior part. And what I'm trying to say is acquiring the expertise is the underlying correlate, or what really brings it is the gradual shift from frontal-based performance based on frontal circuitry, neural circuitry in the brain, to scheme-based performance, which is in the posterior part of the brain. Now, what tells us the meaning, what gives us some sort of feeling versus the other, is where these schemes are located in the posterior part. If the schemes are located here, it's about language. If they're located here, it's about tones, etc. About vision, this part was sorted just in the previous talk. Whereas, if we're looking at computations here, they have more abstract form. It's about the comparison and not about what it is that is larger. In order to tell what it is that is larger, is it a stimulus which is tone or which is something else, it has to be accompanied by specific activation of a specific representation and scheme in the posterior part. This is very nice. I'll give a simple example. And the task we've been studying for an embarrassingly long time is this simple task. I like to call it a game, but most people find it a boring game. I don't. So here's the game. You have two tones, and the game is which tone is higher. These are pure tones. They're around 1,000 Hz, but they're not the same frequency. The one was higher. Which was higher? This one. Wonderful. Now I can make you an expert in this task. The idea is you have a first tone, you have a second tone, and I only gave you one example. So just following the same logic, which neural circuitry among either frontal or posterior underlies this processing according to what I suggested? It's a frontal task in a way. It should be, according to what is said, in a way, surprisingly, but this is my interpretation, it's like an IQ test. Why is it like an IQ test? Because it's the first time you probably experience, well, some of you haven't, but for those of you who know it's a novel task, it's the first time you hear it, and you have to compare, because you don't have a recent history or long-term history. And tones, as much as they are simple physically, they're not what you experience in daily experiences. This is not what you usually have, even though it's physically simple, but we don't have the expertise of categorizing these kind of stimuli. So we don't have a pre-made scheme. We actually have to compare. It's very, very simple. What I suggest is that you have to perform it with frontal circuitry, namely retain the first wait, have some activity or some form of representation that will retain this information until the second stimulus is presented, and then do some comparison, which seems simple, but it isn't. We can do this task for several trials, like several dozen trials, but have nothing that is repeated across trials. We have these two tones, and a second trial, these two tones, this is frequency, these two tones, and you have to compare in a way from scratch on every trial. What we can then measure is how good people do this task when you cannot form any useful scheme for this task. And what we find is that with about 10% difference, people do it about difference in frequency, people do it about 80% correct. Now we can have another variation which is very, very similar to this task. However, what we do is from the explicit perspective of the participant, is exactly the same thing. People do not tell that something has changed, but now what we have is that across trials, the first tone is always the same, and the second tone changes. Of course, it's either high or low. We're not cheating our subjects. The specific consistent answer we're not do. But the point is that we have formed a very simple scheme. The scheme is that the first tone is consistent, and the informative tone across trials is always just the second tone. So if you manage to form a scheme within which you have a representation, perhaps a different part of the brain, have a representation of the repeated tone, then you also know not what the second tone is, but the information is presented in the second interval. This is important because you do not necessarily have to retain the first tone until the second tone comes. And if you can use different type of circuitry for when you have representation which is across trials, like long-term representation, like my representation of study space, which is kind of when I identify you, I compare it with some long-term stored representation, then we don't have to retain the information within the trial, and we can use a different circuitry. How do people perform in this case? This is how they perform. These are the thresholds that are measured, namely, they do 10 times better. Rather than having about 10% difference needing to retain 80% correct, they need about 1%. They cannot tell the difference, but they're using it. I'm saying that they're using it, but can I show it? Well, first let me try to convey the idea that we have long-term memory, we all have long-term memory. We have what we call working memory. The working memory is the concept of how long we can retain the information, like from the first tone to the second tone in an accurate manner within a trial. But here, in order to get the regularity, in order to detect the regularity which is repeated across trials, namely that the first one is always the same across trials, we have to have some longer, broader, in terms of time, window within which we acquire information. I call it the contextual window of information. In classical cognitive studies, this has been a largely neglected window of information, but what I'm saying is that this is the window that acquires simple regularities across trials and is kind of a major tool for acquiring basic schemes. Now, we can have another very simple scheme. The second simple scheme is, well, it's symmetric in terms of information. The reference, the repeated tone, is always the second. The first tone changes. Again, it's a scheme. Are we going to be good at that scheme? Do we detect this scheme? Is it well, it's quite a simple regularity. How good are we with it? We're pretty fragile with that. Even though it seems very simple, if this is all we do, namely that for several, like 40, 50, 60 trials, this is consistently what we present. The second tone is always the same, then we do pretty good, about 1%. But very quickly, we can make it difficult so people will not notice it. But first, let's see how we can test whether indeed people use this consistent potential schematic information. So what we do in order to tell beyond the performance, we record ERP. So you already mentioned ERP. What we do is record ERP. Mainly we're looking at small voltage changes around here, and we're looking at ERPs when individuals perform this simple task. So what happens? This is the tracing time. This is the voltage of the function of time. So this is about 1 second. And these are the basic components of the ERP that we can measure. This is called N1. This is negative. This is positive. N1 and P2, these are responses that are emitted by the auditory cortex. This is the response to the first tone. This is the response to the second tone. It's somewhat smaller because there's been some adaptation, because there's been less than 1 second apart between the first and the second tone. This is N2. I don't want to address it, but the interesting part is this part. This is called P for positive, because it's a positive signal when we record it, and it's 3 for 300 because it's emitted 300 after the tone. 300 milliseconds, a third of a second after the tone. Which tone? Now this is one component that has been studied by thousands and thousands of studies, not in clinical but in cognitive psychology. And what we know about P300 is that it's produced when we're looking for some kind of category and this category is identified. So here it's produced when the second tone, 300 milliseconds after the second tone was presented. But what I'm showing here is the condition when the first tone, this is the first tone, is always fixed, is always 1000 hertz, and the second tone changes. So in a way, this is where information arrives, because you cannot tell at this point in time which tone is higher, because this is fixed and this changes, and indeed the categorization has occurred here. So we're using P3 to mark the time when a categorization has been made, whether participants can tell about it and whether they cannot, because P3 is introduced even when an implicit categorization was made. So the question, which is really interesting for us, is what will happen in the case where the fixed tone is in the second position and the informative tone, which changes across trial, is in the first position. Because in principle, if you can get the scheme, the P300, which denotes the moment in time when a categorization was made, does not have to wait here. It can already be introduced before the second tone is really presented. And this is what we find. If you look at what happens after the second tone, there's nothing. Even though this is the point in time at which participants press the key to say the second tone was either higher or lower. This is the point in time they say that they made a decision. They say that they listened to the first one, listened to the second tone, retained the information, and made a decision here. They're not aware of anything that's going on. But the P3 really switched here. So in a way, an implicit decision was made even before the second tone was actually presented. So the idea here is that they really learned that there's nothing transformative in a fixed position and where the information is introduced in time. So they learn to attend the pattern of information and then utilizing it and taking together with the behavioral data, they're much, much better when they can do that. And we can see that it's a really one-to-one relation. It always comes together. It's always when you manage to detect the scheme that you manage to be a very, very good performer.
What happens if you take the two tones further apart? Instead of a second, a few seconds or a minute?
It's a good question. We haven't done it here, but I guess that if you do it consistently, several seconds apart, at some point this memory collapses. I think it's a gradual process, but I haven't done it directly. Right. There's so much that you can stretch it. There is a limit to how much you can stretch it. We can also try to map what areas in the brain change their activity when you manage to form such a scheme. How do we do that? We put people in a magnet, in a strong magnetic field, and we can see whether there's a difference in the distribution of activity when they perform the same task with kind of repetition, and when they perform the same task but it varies across trials, and subtract the two images of the brain and see whether we have areas that are significantly activated more in one of the conditions. And the areas that we mark, of course this is a marking on top of it, and these are, those that are in orange are those areas that are significantly activated more when you have no scheme because you keep changing the trials and you don't have the opportunity to form any scheme. And these are known from other studies as areas that denote the areas of networks that do working memory. What do I mean working memory? That if you look at what single neurons are doing, you can also record the fact that they keep firing, keep the information after the stimulus stimulus has decay, but only when there's a need to retain this information, like in the pom-pom, you have to retain the information in some kind of activity between the stimuli. These are the areas that have this information, and they're only activated, or they're more activated when you actually have to retain it. The next thing we ask is, so what happens? Suppose you train individuals, you have, well, everybody, of course we are welcoming everybody to participate in these studies, but in this case these are students who come into the lab, and they have 80 trials, and we measure their threshold with the reference always in the first position. Then another 80 trials, another 80 trials, another 80 trials, and then you can see they improve. Namely, that the difference in frequency they need in order to attain the same level of performance decreases, so they improve. And now, the fifth assessment, we change in a manner they don't notice at all, in a manner which exactly retains the same stimuli, the same task, the same relevant aspect, but changes the scheme. It's regularity, but now the consistent pattern is that the second term is always fixed. They have to relearn, which means that what made them better is not a specific learning of the stimulus that was presented, it's exactly the same stimuli, not the parameter they were asked to attend to, but the real scheme of where information is presented within the trial. And when you change this position, they have to relearn. And
the rate of learning in both cases is the same.
right.
It's not the case that the second time they learn faster. Is that correct?
In this case, but there's a caveat. You can do it in the reverse direction, and in a way from the harder, there is transfer. My interpretation is that we have some predispositions, even though it's the same level of complexity, we prefer structure where the novel part, let's say this is a sentence. Sentence is composed of two tones, one which is repeated and one which changes. And we have a tendency for preferring the first part of the sentence to be known and only afterwards the novel part, whereas if you do the reverse, it's somewhat more difficult, but we get full transfer. And there's also a very similar structure in language. In discourse, when people look at how people structure their sentences, there's a strong tendency for the first part of the sentence to include the part which is known, and the novel information is presented almost always across languages at the second part of the sentence. If you look at long-term learning, you get specificity of learning in both directions. These are individuals that kept on coming. It's not the same scale, so they're doing better, and they keep improving across days, and learning is specific in both directions. What I'd like to say is that the same simple idea, but of course in a much more complex way, applies also for language acquisition. One of the things that has been the hallmarks of language is syntax. What does it mean, syntax? That the order of words affects the semantics. And there's lots of the traditional, almost traditional syntax theory, mainly initiated by Chomsky, is that there's something innate in how we represent the basic structure of the function in the sentence in a hierarchical tree-like manner. I'd like to suggest that we are looking again at scheme-based acquisition, and we have difficulties when these schemes are violated. What do I mean by that? Let me give you a simple example of a sentence. The girl kisses grandmother. This is a simple sentence in the sense that this is the subject, this is the verb, okay, and this is the object. This is simple, and this kind of sentences children pick up and can understand by the age of 2 or 3 or something like this. Namely, if you have these two pictures and you're asking, well, okay, point to the picture that matches the context of the sentence, you'll have even a 2-year or 3-year-old kid can say, this is the right description. Similarly, you can make it a little bit longer, but same level of difficulty. The grandmother that kisses the girl. This is fine. What I suggest is that this is the kind of scheme that you first structure, which is kind of, you expect this is the subject that does, the person that does, or the entity that does the verb onto something. This is the basic scheme that you structure. However, this is violating this simple scheme. The grandmother, that the girl kisses. You're trained to expect. This is the scheme. This is a much more difficult sentence to understand. This takes kids to reach the age of 5 to 6 to understand, and some kids who have language disability do not manage to understand that also by the age of 5 or 6. Which areas in the brain are going to be activated by these different sentences? So, here is a recent from the last 6-7 years. This is again, well, a colored picture of the cortex. These are areas that are associated with language comprehension and production. So this is area called Wernicke, named after the neuropsychologist that first identified this area in the 19th century, and this is associated with language comprehension. Traditionally, this is the frontal area, okay, named after Broca, and traditionally associated with language production. However, recent studies found that there's also a distinction between what type of sentences activates which area. And it really follows exactly the same pattern. When the sentence violates the scheme, so the scheme of I'm the performer, I do something on that is violated. So it's the girl that the grandmother kisses, Broca's frontal area is activated. And in a way you can make it a little bit even more complex, and then you can see that even more frontal area is activated, which suggested that the distinction is not like this is just motor part, as traditionally thought, but this is what's activated when the schemes cannot reliably perform the task. You know, if something is violated and you have to do online comparison with which we're typically poor and we're not too good in understanding these sentences. There's also a difference in the level of ability that different individuals can acquire these regularities and these or form these schemes. What I'm suggesting is that individuals who have difficulties in detecting regularities in sequences of sounds, whether speech sounds or other sounds, will also be more susceptible to develop language disability. Developing language disability meaning that they are not as sophisticated with language usage as their peers. It turns out exactly that these are individuals that have difficulties with the kind of sentences that violate the basic scheme in syntax that I suggested. A similar case is the case of dyslexia, and this is our finding, and what we suggest is that dyslexia, which is a difficulty in acquiring adequate reading ability, but typically is associated with linguistic difficulties. We think of reading as something visual, but actually read for words. We read for consistent mapping between sequences of visual symbols, sequences of letters, and sequences of syllables. And what we suggested is dyslexic individuals have difficulties in picking up these regularities that are embedded in language, but not only in language, it's the same type of difficulties that they have difficulties that they do not detect as efficiently when presented in simple tones. And we did the same experiments with individuals with dyslexia. These are their peers. We did the same task that I presented, I started the software. You have two tones, you have to say which one is higher. This is very simple. In one case, there is a standard tone that repeats across files. The other case, there's no standard, and this means that they need a larger difference. It's more difficult in order to attain the same level of performance. They need to have more different stimuli. This is a control. When we look at dyslexic individuals, what we find is that they do not benefit from having the same tone repeated across files, from having the standard, or in my notation, they do not manage to quickly form an effective scheme from the repeated sequence of sounds, and hence they do not manage to do lots of things. For instance, they're more sensitive to environmental sounds. The idea, or my interpretation, to being more sensitive, they have a harder time sitting in a noisy cafeteria and tracking a conversation, is, well, in the first second they have the same amount of difficulty. Everybody has. But other people track the consistencies and regularities that characterize the speaker, and they're not as effective in tracking these consistencies Namely, they're not as effective in pulling the signal because they know what they want to look for, or implicitly know what they want to look for. So it remains very poor signal-to-noise ratio because they cannot track these regularities in sounds in various aspects of the sound, and similarly in aspects of the language. Last part I will talk about, and this is relates to Ellie's talk, is I've been talking about large-scale theories regarding pretty complex stuff, but do we know anything about the underlying mechanisms at the level of single cell, single neurons that decode these consistencies? Yes, but very little. This is a short answer, not a longer answer. One of the tools that has been shown very effectively, it's been discovered like 25 years ago by a Finnish psychologist named Nathanael, and since then it's been a very, very productive line of studies. It's called the mismatch negativity. What is the mismatch negativity? It's a signal that you measure using ERP, namely looking on the skull, looking at very small voltage changes on the skull, and it is a signal that is mainly emitted by the auditory cortex. And the nice thing about it is that you can watch a film, do whatever you want, well, as long as it's a silent film. Maybe it's a little boring, but you can watch a film. And meantime, there's a series of sounds that is presented to you, and the person presumably doesn't pay attention to the sounds or pays attention to something else, and you can sort of tap in a way the automatic mechanisms that track the consistencies and see what kind of consistencies this person tracks. It's called mismatch negativity for the following reason. This is how it works. Well, as you can see, it's not like chess. It's kind of a primitive chess version. So there's a series of tones, they're all the same, there's the 1000 hertz, and then there's an oddball, okay? So this is really a primitive way of regularity detection. As primitive as it gets, but in a way as fancy as we can understand it. And so after a series of sounds, there's an oddball. And if you look at the response to these sounds, you have a small response. This is a small response recorded here with this electrode. And then when there's a deviant tone, there's a large response. It's called mismatch negativity. It's called mismatch because we implicitly expect what has been going on so far, to continue forever. And then there's a mismatch because there's a deviant sound, because it deviates from the very, very simple pattern of what has been the last sound will be the next sound, And this poof creates a larger response, and mismatch negativity is the difference between the response to the repeated tone, which is not surprising, which is boring, and the amazingly exciting, surprising tone, which deviates from this very, very simple scheme. So we can look at what happens automatically in a way, at least with this kind of scrutiny. For this kind of scrutiny, we have some simple models of what's going on. Why is it that we have a deviant response to this time? Well, the simplest explanation is if we look at the pattern of responses of simple neurons in the auditory cortex. The auditory cortex is, let's say, somewhere inside here. And we look here, you can look like that. This is frequency, there's frequency tuning, namely their responses, the degree of their response as a function of the presented stimulus frequency. This is a neuron, very schematic representation of the response pattern of neurons that best prefers 1000 hertz. This is a neuron that best prefers 1400. And they have a tuning curve. What does it mean that they have a tuning curve? That if you present a stimulus that deviates in frequency, they will respond less. But it's a relatively broad tuning curve. Namely, that if it deviates for about 10%, they will respond less, but not nothing. So the idea is that, okay, they have a response tuning, so they're activated, these kind of neurons are activated every time you have a pop, 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 pop. However, their response decreases as a function of their activation. So if they're pop, 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 pop to the same stimulus after many trials, they respond less. What happens with these neurons? They are not as activated by this stimulus. This is their degree of activation by this stimulus. So they will not be as adapted. Namely, when they have their best frequency, they respond more than this kind of neurons when they have their best frequency because they're not as adaptive. So this is the basis for the interpretation, simple interpretation of the deviant response. Okay? Which means we'll get deviant response only for the kind of parameters that we have very simple tuning for, so they're kind of gradually adapted, and then it's kind of going out of adaptation is what we see when we have a deviant response. This kind of very simple explanation attributes all kind of sensitivity to repetition to the characteristic of single neurons that are more or less adapted and are then going out of adaptation. Of course, if it's a smaller degree of deviation, then the amount of response will be smaller because they're almost as adapted, etc., which means that this predicts that there will not only be a deviant response, but the response to the deviant will also depend on the amount of deviation. The larger the deviation is, the more you are away from adaptation, the less the neurons are adapted, and then you'll get a gradual response that increases as a function of distance from the adapting tone. Okay? If you look at the responses of individuals with dyslexia, these are the mismatch negativity, these are already the differences. In blue you have the...
Are these the people with dyslexia or...?
Red? You know, you're not the first person to ask. I keep changing the answers. I don't know if they're dyslexics or not, but the reason for their being here is not for being dyslexic. This is my collaborator, Leon Buell, and this is the person who's done this experiment. It's a good question. I don't know if she's dyslexic, but we have a schematic representation of the dyslexics, which I've heard for the talk, which is their mismatch negativity response. And for that matter, controls are blue, and the dyslexics are in red. And these are three different levels of deviation. This is the largest deviation, this is the smallest. So you can see that the mismatch increases with increasing degree of deviation. And what you can see is that dyslexics do not detect automatically, as revealed by their mismatch response, the small deviation. They're not sensitive to this small deviation. So this is interesting because dyslexics are identified by having difficulty in reading, and you can in a way reduce the level of difficulty to basic automatic processes that are not as sensitive in detecting simple deviations from simple regularities in a train of tones. Okay? And this is what we see here, just to see how you do it. How many deviants were there? I leave you wondering. So the idea is that people are watching a movie when you have this, and what you're looking at is the automatic detection of the system of this small degree. There were three different levels. There were three deviants, one 10%, one 5%, and one 2.5%. So it's kind of confusing, but there were three of them, and this is what we're measuring: how automatic processes are functioning, even when individuals cannot report. And this is when you were aware and looking for it. This is not how we do the experiment. We do the experiment looking at the Charlie Chaplin scale or something like this, and this is the response of the system. Last piece of information I want to talk about is, so I've already said that we have sensitivity to the repeated tone, and there's a larger response, the larger the deviation, which is easily explained by simple adaptation mechanisms, whereby you have neurons with response sensitivity around these different frequencies. There's another question that we can ask, and this is sensitivity not just to degree of deviation from the average or from the frequent tone, but sensitivity to the variability around this frequent tone. So what we did here is we, rather than have this fixed repetition, we had very, very mild changes around this fixed tone. And we were wondering whether the response to the deviant will be affected by this very, very small variability. If you think about the adaptation mechanisms that I've introduced before, they're not expected to be affected because the deviation is very, very small. It's smaller than their resolution. we can test it, as I'll show you. The question is, once there is a deviant response, will the response to deviation be the same whether there is variability or there's no variability around the repeated tone? And the answer is, first, that indeed, if you look at the responses to the standard, it doesn't matter, you follow the point is that you have to see that these lines are overlapping. The fact that these lines are overlapping means that the response to the repeated tone is exactly the same whether it is fluctuating or not, meaning that if you look at the response to the standard, it seems that the system is insensitive to whether it's viable or not viable because the degree of adaptation as revealed by this response does not differ. If you look at the response to the deviance, well, first let's look at the response to the different amounts of deviance. This is a small deviance, this is a larger deviance, this is even a larger deviance. And this is the difference between these two responses, which is the mismatch, the difference in response between the deviant and the repeated standard. And now what happens when the standard is a little fluctuating? And what we see when the standard is fluctuating is that the response, it seems small, but it's highly significant, and the response is not the same. This is the response when this standard is deviating. This is when it's not. This is a small deviation. This is an intermediate level of deviation, and this is 1 octave apart. This is a deviation from 1,000 Hz to 2,000 Hz. The mismatch response is very large. It's very unexpected because it's really a large deviation, but there's no difference whether it's valuable or not valuable. Which means, if I just summarize, that the sensitivity to the deviance, this is one thing, but there's also automatic recording of the variability around this repeated pattern, but it's not just an automatic recording of the variability, it is scaled with the total range of stimuli, because the sensitivity to the variability is large when the deviance is small, it's smaller when the deviance is intermediate, and it's actually disappearing when there's large deviance. So in a way, there is sensitivity, automatic sensitivity to this variability with respect to what's considered a large deviation. What is a large deviation? With respect to what are the deviations within the stimulus. So we have automatic recording of the average and of the variability around this average. Can we account for this sensitivity using these simple explanations of tuning curves of these single neurons and they're being adaptive less or more? No. I'm not playing with it, but you cannot. Maybe Eli will say more about it. So just take my word for it. You cannot, which means that even for these very simple phenomena of like regularity detection, not just the average, but kind of simple variability with these repeated tones, it's kind of the limit of where we understand the underlying sort of local underlying mechanisms of regularity detection. So if I just summarize, we're very good at regularity detection, probably because we have some predispositions for some kind of regularities to be more salient to us because we're in a way automatically, these are default regularities we're seeking for, but these simple mechanisms are kind of, at least on a short scale, crashing very quickly. Probably what happens is that we use, this is my interpretation, frontal mechanisms to detect more complicated, or when our sort of simple scheme detection mechanisms fail, okay, there's some kind of novelty, we have to figure out what's changing, maybe we have to switch something in the system, in the representation of the scheme, it becomes a frontal task, and then we have to rewire our way back to form new schemes, more complicated structures, which means if we have more complicated structures, probably interplay between posterior and frontal parts of the cortex. The other thing I wanted to say is the success of these mechanisms differs between individuals, and we can track the ability of different individuals in the effectiveness of their simple tracking or tracking of mechanisms of regularity detection by basic automatic mechanisms, and sort of in a way gradually follow them to where they fail in tracking complex regularities, and the example of reading and the understanding of neural mechanisms is in its earlier stages, and there's a lot to be desired. Thanks.
Thank you, Merav. I just want to remind you that the reason for bringing this line of show it to humans, and we want them to identify irregularities, novelties, and so on, or, on the other hand, replace humans by some sort of sophisticated algorithm. I know that taking it to the auditory domain is to sound you moving out of the familiar territory and sounds very strange. But we really believe, and I think we're going to see that even more in Eric's talk, that the fundamental mechanisms of novelty detection are universal. I find it very illuminating to try to understand what's really happening when we see novel events, even on this relatively simple task of deviant detection in two tones. You already see that what we call regular and what we compare it to, and when do we detect irregularities, is something quite mysterious, and I don't know. So even if it's maybe a bit confusing, I hope that by the end of the day, even the video synopsis people will understand.
Think about moving auditory event in time and superimpose them on top of each other, what will look like.
Yeah, and I say it especially to the Shmuel because I'm still disturbed by the fact that you destroy time completely. Whether time, how important time is for our perception.
No, you see, I don't destroy, I destroy time between events, not inside the event.
Yeah, okay,
inside the event time is...
That's very important. Okay. So keep it in mind, have coffee, and have another talk on related but slightly different topic. And then we can go back to video for the rest of the week.
Yeah.
We need to listen to the microphone as well.
Very nice.
I have a question for you, but now we stop it on the very interesting for me because it's another area. And you don't hear what's here when I presented my project, which is more than 40. But my question was, I'm looking for regularity in abnormal parts in lots of data representations. When what we are doing is clustering together the data in order to find regularity of them.